When we have our data, central tendency will give us an idea of the center of the data. With that comes the idea of expected value. So if we have this data set, if we choose a random value, what do we expect to come out? So there are going to be two ways that we look at measuring this. We're going to look at median and mean. And what we'll do is talk about is when is one better than the other in terms of measuring this expected value. So median is a location in the data. It's the middle data value. So there's nothing really to calculate with the median. In fact, we don't really say calculate the median, we would just say find it. So first thing you should always do is make sure that your data is in order. So smallest to largest, or largest to smallest. Then what we're going to do is, if we think about our data as a block, what we want to do is find this cutoff point that leaves it so that we have 50% of our data to the left and 50% of our data to the right-hand side. So it's going to be this balancing point between the lower and upper half of the data. So there's going to be two ways to do this. It'll depend on the number of data values that we have. If we have an odd data set, the idea is going to be we want to have some sort of way of moving towards the middle. What we could do is kind of take off a value from each side. In fact, it's hard to show on this video because you can't see my hands, but I often use my thumbs and kind of go towards the middle, meaning I would do something like cover up both of those and then extend that further and extend that further until with an odd number of data values, you're going to end up with a single value in the middle there. So in one way or another, you want to end up taking off values from both sides so that it's balanced. And from there, we can see what our middle data value is. So what we can see here is we get a value of 12. So in this case where it's actually the data value, I kind of think of it being absorbed by this wall. And what you can see is we have two data values to the left, two data values to the right. So we have this balance with 12 being counted as the median. So with this case, we would have the median equals 12. With even number of data values, we're going to do the same thing, kind of cover up both sides, cover up, until we end up with, if I keep going, it's not going to be balanced. So what I get stuck with when we have an even number of data values is you end up with two numbers at the kind of center of all of this. So our median is actually halfway between these values. So this wall of the median that separates the lower and upper half of the data is in between 12 and 15. So what we want to do is use the average of those two numbers. So what we'll do is we'll take 12 plus 15 and then divide that by 2. So if we calculate that, it'll give us a median of 13.5. So when you have an even number of values, you're going to have to use an average of two numbers. But then we can see how this is a balance of, we have 3 data values to the left, 3 data values to the right, so we have this balance. It's just that our median is actually not a data value from our set, but between two data values. So that's our median. Another way of finding center of our data is using the mean, which is another word for average. And this will be a calculation. So this we need to find using some math. So with this, what we're going to do is add up all of the data values and divide by how many there are. So we've talked about this notation a little bit, but population mean, we use a symbol mu. Typically that will be given to us. We'll rarely be calculating a population mean because having population data to begin with is really difficult. Most often we'll be using the symbol x bar. for our sample mean, since most often we'll have sample data. Now, in terms of a formula, it looks like this down below here. So we have this symbol, which is sigma x, and then divided by n. So let's talk about what these pieces are. X just represents the data values, and n is sample size. And that sigma, the symbol sigma there, so that's sigma as a symbol. And what that tells us to do is add. So that sigma is actually a function used in mathematics. So how this would be read is in the numerator, just is telling us to add up the data values. And then we're going to divide by our sample size, or you can think of that as the number of data values. So I wanted to show you this notation because it's a common form of writing the mean. However, how it translates is something that we're familiar with, of adding things up across the data set, then division of our actual sample size. So let's see this at work. We have two data sets here, 3, 8, 12, 15, 18, and 20, which is actually our data set B from up above. So for the mean, if I write this out, what it will look like is in the numerator, I'm going to add up the data values. So 3 plus 8 plus 12 plus 15 plus 18 plus 20. And then I'm going to divide by my sample size. So for this data set, sample size would be 1, 2, 3, 4, 5, 6. So we're just counting how many data values there are, and that'll make the denominator. Now to jump over to a calculator, show how to plug this in. Here I am at the Desmos Scientific Calculator. There's this fraction button, which is really nice, and this will make sure that order of operations is carried out correctly with this. So if you hit that fraction button, it'll separate a numerator and denominator, and then you can write it just as we wrote on the paper. And then divide by 6, and there's our value of 12.6667. We'll round this to 4 decimal places. That's the general rule that we're going to use in our class throughout the term. So an average of 12.6667. So that would be our mean. Let's do this again with this next data set. What I want you to see with this is how it changes. From the only piece I changed is that data value of 20, I changed to 205. So let's see how this changes the mean. So taking the mean in the numerator, I'm going to add up our values. And in the denominator, divide by how many there are, which we still have 6 values. So what we can see is that we are adding on a much larger value into the numerator. So if I hop over back to Desmos, if you still have your work in here and you're just changing a value, you can actually just edit without having to type it all over again. And then we can see this mean of 43.5. So let's see how this changed, especially keeping in mind that we're wanting to use mean as the idea of center. So if I think about where the mean was in the first case, that 12.6667, or about 13, it was pretty much in the middle. That's a good measure of center for this data. You can even see it's fairly close to our median that we saw in B. Our median was a bit larger, but fairly close by, especially just drawing a line, very similar location. We get to data set B, 43.5 is out here, which is very skewed. It's not a great measure of center for our data, and this is a little strange with such a small data set. However, we want to recognize that maybe this 43.5 isn't a great measure of center for this case, just because of that one extreme data value. So that's something we're going to think about with our data sets is it's really the mean. When is it a good measure of center? It's going to come down to if there are outliers, which this 205 looks definitely like an outlier in this case, or if we see our graph, we can look at the skew of the data. So let's look at a visual in terms of a skewed data set and how this affects mean and median. So this right here is box office earnings from Hollywood movies. And what we have here is a dot plot so we can see more of what's happening on an individual basis. And let's see how the mean and median would compare. Now, when you have a graph like this, if you need to estimate where the median is, typically you can look for the peak of the graph. It should be close by there. So if I think about the general trend of this graph, I have kind of most of my data there, and then we have a data that is very right skewed coming through here. So with that, if I estimate the peak, I'll say the median is about there. So median, and let's say that's at around 50. So the mean, how it's going to change is it'll be similar to what we saw in dataset B. We saw the mean go way up, and it's because in the numerator we're adding these large values. In fact, with a data set like this, even though it's quite small, this would be something that's also right skewed because of this large value on the right-hand side, similar to what's happening in this graphic right here with these large data values to the right-hand side. So what this does to the mean is that it pulls it to the right-hand side. And this is part of the wording for why we call this right skewed, is it's this effect on the mean in that our mean is getting skewed to the right-hand side. So if I had to estimate where the mean is, and I'm just going to estimate, let's say it's close to 200 here, the mean would get pulled to the right-hand side because in terms of the calculation, we'd have these large data values being added in. So what we need to think of is, what if I had a movie coming out this year in Hollywood? In the year that this data was collected, let's say we chose a random value, what could we expect? What do we want to use as our center? So if I was interested in the expected box office earnings for just a random movie, well, we have these two measures of center, and we want to think about which is a better measure of center. Basically, when do we want to take into account these outliers? Because right now our mean is skewed. Our median is more in line with what's happening for most of the data. So we can imagine is for this year, these movies out here are probably those big box office movies. Maybe they're sequels, they have a huge following, or maybe it was a book turned into a movie. They're special cases. They aren't behaving like other movies. So if we're talking about some random movie coming out that year, it's not going to behave like those outliers. So really, in terms of center, we don't want to include those outliers. Those outliers would skew our expected earnings. So saying this 200 wouldn't be accurate because it would be giving them a larger value than what's happening for a random film coming out that year. So because of this skewed data, which leads to a skewed mean, we would want to use the median to describe expected box office earnings. And basically we want to use a value that's not skewed by these outliers or even just this tail of data. So something we want to keep in mind is that the median is resistant to outliers. It's not going to be affected because it's just a location. If I went back to these two data sets here and talked about the median, it actually wouldn't change. For this first case, data set A, the median we found up above there was 13.5. If I found the median for data set B, it would still be at 13.5. So it would ignore that outlier, which would be okay for this idea of center. So the mean is going to be affected by outliers, and more specifically, it's going to be skewed by outliers. and the skew of that mean is going to follow the skew of the graph. So that's where, when describing our graphs, we want to talk about where the tail is, because that's where the extreme values are, and that's going to move the mean in that same direction. So let's see how these line up, how mean and median change based on the shape of the distribution. So if we have a symmetric distribution, if we're wanting to estimate the median, let's start with just that. It'll be near the peak of the graph. So let's say there's our median, there's our median, there's our median, close to the peak of the graphs. Then how the mean will change, well, if it's symmetric, they should line up, or at least be very close by together. So that's what we saw in data set A in our example down here when we calculated mean. They're a little far, but close enough that we'd have a roughly symmetric distribution there. Then if we go to left skewed, so this would be a case where we have these extreme small values, and so our mean, which would usually line up with our median, ends up getting pulled to the left-hand side. So it gets skewed to the left. So when we have skewed left distributions, our mean ends up to the left of the median. It ends up being skewed to a smaller value than what's happening with the median. And skewed right, like we saw up above there, would skew the mean to the right-hand side. So the median is pretty fixed in terms of where it occurs because of the location, but the mean moves around based on the values in the data set. So for a symmetric distribution, mean and median should be about the same. For a skewed left distribution, the median should be larger than the mean. And then for a skewed right distribution, the median should be smaller than the mean. And this is something we can use if you're looking at the graph and are unsure of how to describe the shape. Compare these numerical values. Look at the median, look at the mean, and see which of these cases does it follow. So with this, when we get to writing our description, we're going to start by describing shape, and then our next piece is to describe center and spread, and how we do this is going to depend on the shape of the distribution, because if it's skewed, we don't want to talk about the mean as the center of the graph. So we're going to end up with these two branches for describing center and spread. If it's skewed, then we're going to describe the median as center, and then for spread, which we'll talk about in a following video, is going to be the interquartile range, which is going to be based on a similar process for how we find median, and then it's going to be more location based, and it's going to ignore those outliers, which is what we want for this overall idea of center and spread. When we have a symmetrical distribution, then our mean is a fantastic measure of center because it does take into account those values, but it isn't being skewed one way or another by outliers. So with symmetrical distributions, we'll use mean for center, and then we'll use something called standard deviation to describe spread, which we will calculate in a following video. But that's the idea of central tendency using median and mean, and how we find that value, then in describing our data, which is the best fit based on the shape of the data.